This is Knowledge Engineering with Semantic Web Technologies. Lecture number 4, OWL, Rules and Reasoning. This is the extra part number 13, Semantic Web Rule Language, SWRL. So today we want to talk about how to imply or how to engage rules in the semantic web together with ontologies. Okay, what is SWRL, this Semantic Web Rule Language? It's nothing else but a combination of parts of OWL ontologies and rules which are taken from data log. And the language to write data log expressions as a markup language, that's then rule ML. So rule ML is an equivalent to data log as a markup language here. Okay, so what we do is we apply data log rules on OWL ontologies. So simply symbols in rules can be here OWL identifiers or new data log identifiers. So this is the basic concept simply behind SWRL. There already has been a W3C submission 10 years or more than 10 years ago in May 2004. So it's a rather old language which does not right now exist as a standard, but only as a submission. But nevertheless, you will see SWRL is part of many tools within the semantic web. So this is also the reason we are now talking about that. So concerning the syntax, there are two variants. For example, you have an XML-based variant and you also have an RDF-based variant and also a so-called abstract syntax. So there are three syntax variants. And for the XML-based syntax, we will see an example. And for the abstract syntax, you will see that you already have seen examples for that. In SWRL, rules usually are represented, as you know it, from body and header, but they are called differently. Here they are called antecedent, which is the body, and consequent, which is the header. And what we always should keep in mind, SWRL is undecidable. And we already know that. So when we have talked about data log, we said when we combine data log together with OWL ontologies, then the result is not decidable anymore. So why then is this part of really practical applications? We will see that in the end of this part of the lecture. Okay, let's have a look at the language and how it works. So we said rules in SWRL are usually expressed as antecedent, then we have the implication, and then we have the consequent, which are body and header. From which parts can body and header consist of? So the antecedent and consequent usually are conjunctions of assertions. These assertions are also called atoms. And they can have the form, for example, C of x or P of xy, which of course refer to class expressions of OWL or property expressions in OWL. And they can also, for example, be same as or different from expressions referring to variables or individuals here, where x and y are usually variables. They can also be OWL individuals, or they can be elements of so-called OWL concrete domains, which are nothing else than typed literals. But they have to be distinguished simply because then when we express semantics, we have these three kind of things that have to be distinguished. And of course, C of x is an OWL class description and P of xy is an OWL property description. Okay, so a SWRL rule looks the following way. Usually they are written the other way around. You also have seen this when we have talked about rules. So here the header is referred to first, and then the implication arrow simply is turned around. It changes direction, and then you have the body. So A here is the header. Usually it's one header element, and then you have a conjunction of elements which are here in the body. They are referred to as B sub 1 to B sub n. And then a SWRL knowledge base, K, is nothing else but sigma pi or sigma p, and sigma is an OWL knowledge base and p is a finite set of rules. And the atoms of which a rule consists in the body, for example, they can be here class expressions, they can be data type expressions, they can be object properties, data type properties. Then there is something special in SWRL. There are so-called built-in functions. They usually refer to P, which is the name of the built-in function, which can be, for example, a string manipulation function or something else. And then you have specific variables, data type variables or value identifiers on which you apply this built-in function. And then you also have the possibility that an atom can represent a same as or a different from expression that you see here as I equals J or I does not equal J. So this usually are the so-called SWRL atoms. What about the SWRL semantics? So how do we interpret that? So first of all, OWL, DL, description logics, and data log, they should be applied or that they should use the same interpretations. Otherwise, it might become complicated. So therefore, OWL individuals are treated like data log constants. So they are treated identical. So what about classes? OWL classes, of course, are identical to so-called unary data log predicates. And OWL properties, yeah, they are then, of course, treated as binary data log predicates and vice versa. So individuals become constants, OWL classes become predicates, and so unary predicates and OWL properties become binary predicates. And then the interpretation can be a model for an OWL ontology as well as for a set of data log rules, which means entailment for this combination of OWL and data log might be possible. Okay. So let's define an interpretation for that. So in an interpretation for SWRL, we need the following components. So first we have delta I, which is the object interpretation domain. Then we have also a data type interpretation domain. So we here separate object from data type. So object properties, data type properties. And then we have, of course, interpretation functions for objects. I is the object interpretation function, and then we have D as data type interpretation function. And usually, of course, the two domains, object interpretation domain and data type interpretation domain, they have to be disjunct. So that's the usual stuff. Then, of course, we also consider variables, and we also distinguish here between object variables. This is y sub ix, and they are, of course, taken, or they are mapping to the object interpretation domain, individuals which are there. And we have v sub dx, which are data type variables, and they are mapped to the data type interpretation domain. So what about the SWRL atoms? So here you see the interpretations for the SWRL atoms, and this is straightforward. So if the individual I is of class C, then the interpretation of that would mean that the interpretation of I, the individual I, is an element of the interpretation of the class C. And it works the same way for object properties, it works the same way for data type properties, it works the same way for data type definitions. Then you have here the built-in functions, the same as and the different from expression. So this is the way how we define a simple SWRL semantics. Okay. But of course, now we have to define when is a SWRL expression satisfied and when not. First, we are looking to the antecedent. When is an antecedent satisfied? It's satisfied simply if it's either empty, so this would be trivial, of course, from the empty set I can, of course, then imply everything, or all atoms of the antecedent are satisfied. Then, of course, the entire antecedent is satisfied. Next, let's have a look at the consequent. The consequent is satisfied if it's not empty. If it's empty, then of course it's not satisfied, because then we are implying something which does not exist. So it's not empty, and in the same way, the atom, so usually it's one atom, of the consequent is also satisfied. And now we can say when an entire SWRL rule is satisfied for an interpretation I, it's satisfied if and only if the interpretation I, which satisfies the antecedent, also in the same way satisfies the consequent. And this is what we need for a SWRL semantic. So it's pretty straightforward, as you see here. Okay, let's have a look at an example. So here you see the rule first expressed in an abstract syntax. So we say here has uncle x set. This is the rule, so let's read it the other way around. So if x has parent y and y has the brother z, then x has the uncle z. So this is an uncle expression. And you see here in the yellow box the same rule expressed as a SWRL rule in the XML-based syntax variant. And you see here we are using rule EML, so rule ML, so this is the rule markup language, and here we are defining an implication, so we are defining a rule. First we have some metadata about, so what's the URI of that rule that we are referring to, then we have an annotation and documentation part, and then comes the body. In the body part we define the atoms which are then connected conjunctively. So the first is an individual property atom, and here we say it's the property atom which has the name hasParent. And then we say, okay, there are two variables, x and y, which are connected by a hasParent. And then the next one is hasBrother, and there we have y and z, and these two then are conjunctively connected, usually being in a body of a SWRL rule. Then comes the header, and in the header we only have usually one atom. So here we have one individual property atom, which here is the property hasUncle, and which consists of two variables, x and z. And then you close all necessary tags, and this is the SWRL rule expressed in the XML syntax. So you see this is of course quite a bit expensive in terms of writing, but you see it's quite easy and simple to express. Okay, what remains is, what we already know, SWRL is undecidable. So if we combine OWL and SWRL together, so here usually logical inference is undecidable. We cannot simply say that an algorithm really comes to an end if it tries to check consistency. So at least not for all expressions. So there is no known algorithm that is able to entail all possible inferences for all SWRL knowledge bases. Yeah, but on the other side, it means also if you really would engage an unlimited amount of resources and time. But from a practical perspective, if you look at it, yeah, there's a benefit, of course. You can limit the number of inferences you consider, and you can say there are algorithms which are able to entail all possible inferences from some SWRL knowledge bases. Likewise, there are algorithms that are able to entail some inferences for all SWRL knowledge bases. And simply for them, it's practical to work. So you simply have to keep in mind, of course, it will not work for all possible situations, but in practical life you can use it because, you know, yeah, some of the inference algorithms work, some inferences are possible, but not necessarily for all knowledge bases that I have, or if I restrict my knowledge base, then possibly all inference will also be possible again. So this is the trick. If you want to apply SWRL, there are several kind of reasoners that you see here. So there is a list of reasoners. So for example, Palette is a reasoner, a well-known reasoner, which includes SWRL. And we also have already had this demo together with Protégé, with the Protégé tool. And in the Protégé tool, you also have a tab here for rules. You see this in the bottom line under the purple box. You see here rules that we have already in our example defined in SWRL. So these are SWRL rules, and they can be applied, and the reasoner is able to make the according inferences and deductions for exactly these rules. So this is possible in Protégé, for example. Okay, but we won't go deeper into that. Just keep in mind, SWRL in general is undecidable, but if we look at fractions, they might be, again, decidable. And this is something what we want to cover in the last part of the lecture. In the last part of the lecture, we will have a look at rules which are already expressible in OWL, so which means these rules then are decidable.